We now discuss the solution of a problem from the section Group Theory, and this question has appeared in the CSIR National Eligibility Test held on 16th September 2022, and the given problem is related to the number of elements of order 7 in a group G in the given context of the question given in the examination paper. The given question is, let G be a simple group of order 168. How many elements of order 7 does it have? We are given 4 options. Option 1, 6, option 2, 7, option 3, 48, option 4, 56. We have a group G of order 168 and it is given to be a simple group and required to find the number of elements of order 7 of the group G. We now discuss the solution of the problem in detail. We are given a group G and the order of G is 168 and G is given to be simple. Now order of G is equal to 168. Write down its prime factorization, that is equal to 2 cube into 3 into 7, and we are required to find the number of elements of order 7. So it suggests you that you talk about the silo 7 subgroups of G. Note that 7 divides order of G and 7 square does not divide order of G. Then we recall Silo's first theorem. By Silo's first theorem, G has a silo 7 subgroup of order 7. Agreed. We want to count how many such silo 7 subgroups are there. For that, we recall Silo's third theorem, which says N7 denotes the number of silo 7 subgroups, and it is given by N7 is congruent to 1 mod 7, and N7 divides that part of the order of G which is free from 7, that is 2 cube into 3, that is 24. So these two conditions must satisfy this N7. So the first one we will see, N7 is equal to 1, 1 plus 7, 8, 8 plus 7, 15, etc. And N7 should divide 24. So now out of this 1, 8, 15, etc., which of them divides 24? That will be N7. That N7 will be 1 and 8. Agreed. If N7 is 1, then G is not simple, which is a contradiction. Why? G is given to be a simple group. But if you take N7 is equal to 1, then G will be not simple. How? N7 is 1 means that there is only one silo 7 subgroup is there. When it is only one, then we have a theorem that it says it is normal in G. That means G has a non-trivial normal subgroup of order 7. But G is given to be simple. What do you mean by simple? A group G is simple if it has no non-trivial normal subgroups. But now G has a non-trivial normal subgroup, therefore it is not simple. And it's a contradiction to the fact that G is simple. The reason is written here. That is, if it is only one, then it is normal. When it is normal, non-trivial normal, it is not simple. So, therefore, n7 is equal to 1 is not possible. Therefore, n7 is equal to 8. So, this proves G has 8 silo 7 subgroups of order 7. We continue in the next slide. That's what we have done so far. Now G has 8 silo 7 subgroups. Let us take any one of them. Why not we call as H? Let H be any silo 7 subgroup of order 7. Then H is cyclic. Why? The order of H is 7. 7 is prime. Every group of prime order is cyclic. Therefore, order of H is cyclic. When H is cyclic, it is generated by a single element. Then, except the identity element, all other elements of H are of order 7 because 7 is prime. So, then H is cyclic because order of H is equal to 7, which is prime, and every group of prime order is cyclic. And further you note down each non-identity element except the identity element, every other element is of order 7. Agreed. So that means H has 6 elements of order 7. So out of 7 elements, leave 1 element, the remaining are 6 elements are of order 7. This is with respect to H is any silo 7 subgroup. That means every silo 7 subgroup of order 7 has 6 elements. And how many such silo 7 subgroups are there? 8. So therefore the total number of elements of order 7 in G will be 8 silo subgroups. In each one, 6 elements are there. 8 into 6, 48. That's the answer. But one gets a doubt. Maybe if you take 2 different, distinct silo 7 subgroups, their intersection may not be identity. Then in that case, this counting doesn't work. Now further, we note down that if H and K are any 2 distinct silo 7 subgroups of order 7, then their intersection, H intersection K, is identity element alone. Now H and K are any 2 distinct silo 7 subgroups. Therefore, H intersection K is a subgroup of H, is a subgroup of K, and the order of H is 7. So now H intersection K is a subgroup of H. Therefore, by Lagrange's theorem, the order of H intersection K divides order of H, but order of H is 7. Therefore, order of H intersection K is either 1 or 7. If the order of H intersection K is 7, then H intersection K is equal to H is equal to K. That means H and K are equal, but it is distinct. So that is not possible. Therefore, the order of H intersection K is 1. Therefore, H intersection K is just identity element alone. So that means now the counting works. Now the number of elements of order 7 in G. So we have 8 silo 7 subgroups, and every silo 7 subgroup of order 7 has 6 elements. Therefore, the total number will be the number of silo subgroups 8, and in each one 6 elements of order 7 are there. 8 into 6, that is equal to 48. So let's look at our options. Our answer 48 appears against option 3. Therefore, the answer to this question is option 3. That is, the number of elements of order 7 in G is 48. So that is the detailed discussion of the solution of the problem from the section group theory, and it is related to the number of elements of order 7 in the given context given in the question. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.